All right, hello everybody. So today we want to talk about the ratio and root tests. So I'll say here first, consider the geometric series. So we'll have 2/3 plus 1/3 plus 1/6 plus 1/12 plus 1/24 plus dot dot dot. And we want to look at what happens when we go from one term to the next term. So in a geometric series, remember, it's always the same number that we either multiply or divide by. So here we're dividing by a 2 or multiplying by a half. Those are the same thing. So here we're going to multiply by a half. To get from here to here, we also multiply by a half. To get from here to here, we also multiply by a half. And the same thing from here to here, we multiply by a half. So that's a geometric series. We're just multiplying by the same number each time to get to the next term. Okay, so say, since the absolute value of r is equal to 1/2, which is less than 1, remember that means our series converges. Right, whenever we have these geometric series, it's very easy for us to tell whether the series converges or diverges. So we can ask the question here, why does absolute value of r less than 1 guarantee convergence while the absolute value of r greater than 1, greater than or equal to 1, guarantees divergence? So we can ask this question. Okay, so let's look at two different series. So let's say we have series A here, and series A is going to be the sum from n equals 1 to infinity of 2/3 times 1/2 to the power of n minus 1. So remember, whenever we have these geometric series, we can just read off that this is A and this is R. So R is equal to 1/2, so this thing should converge. So the reason here is here the absolute value of R is less than 1. So this thing should converge. So let's just look at the terms in this sum. So here first we're going to have 2/3 times, so if we plug in n equals 1, we're going to get 1/2 to the 0, which is 1, plus, so the second term is going to be 2/3 times 1/2 to the power of 1, which is 1/2, plus 2/3 times a half of that, which is a 1/4, plus 2/3 times a half of that, which is an 1/8, plus, and so on. Right? So that's what happens whenever we have absolute value of r less than 1. And you can see here, each term is getting much smaller very quickly. But if we have series B, so let's write down here series B. And series B is going to be the sum from n equals 1 to infinity of 2/3 times 2 to the power of n minus 1. So here, notice that the absolute value of r is going to be 2, so the absolute value of r is greater than or equal to 1. And here it's definitely greater than 1. So this is the second case that we've run into, and let's just try listing out the terms. So if we plug in n equals 1, we're going to get 2/3 times 1. So if we plug in n equals 2, we're going to get 2/3 times 2, and then 2/3 times, so each time we're multiplying it by 2, so times 4, plus 2/3 times 8, and so on. So you can see what's happening here is actually these terms just keep getting bigger. So as you go towards infinity, as you just keep adding infinitely many of these, your number is going to just start exploding. You're going to get a very, very big number. So this is going to actually diverge because this is going to go towards infinity once you add all these numbers up. Whereas this one goes towards, well, at the end of it, it's going to go towards 0. Each term is going to become closer and closer to 0. But whenever you add these things together, that's not enough to guarantee that you're convergent, but it just ends up being the case that whenever you have one of these geometric series and the limit as n goes to infinity is 0, then that's when we can say that it's convergent. Okay. So I'll just write down in words what I said there. So in A, R equals 1/2. So every term is half the size of the previous term. So I'll say here that the terms are shrinking. Oh goodness, I miswrote this. Shrinking fast, very quickly, in fact, because every time they're getting halved. So the terms are shrinking very fast. So the sum is growing very slow. Right? So that's the reason there. The terms are shrinking very quickly, so the sum is growing very slowly. But let's again look at case B. In B, R equals 2, so every term is twice the size of the previous term. So here the thing is, the terms are growing fast, right? Because every time they're doubling, so if the terms are growing really quickly, so the sum is growing ultra fast. Right? So if these terms are just growing exponentially quickly, then the sum is also going to grow exponentially quickly. So that's why whenever r is greater than or equal to 1, you're just going towards infinity. But if the absolute value of r is less than 1, then that's the case when these terms are eventually going to get infinitely small, and you just end up getting a number. We said that this was equal. The whole thing, when you add together all the terms, we said was a over 1 minus r. Because just as you go, sure, you're adding together infinitely many things, but eventually the terms just get so small that they don't matter. So that's what you get. Okay. So I'll say here, the reason why geometric series are so easy is because the common ratio r because of the common ratio r and how it dictates how fast slash slow, the sum is growing slash shrinking. Right, so that's why geometric series are very nice. So let's say here, a non-geometric series doesn't have a common ratio, right? So that's kind of bad because it doesn't have a ratio that's the same between all of the terms. So it's not quite as nice. But if there is some pattern in the ratio an plus 1 over an, so this is the next term over the previous term, right? So this is a term divided by its previous term is what I meant to say. As n goes towards infinity, we can use it to determine whether the series converges or diverges. Right, so the takeaway here is geometric series are very nice to work with because they've got this common ratio that dictates exactly how they work, and you can say exactly whether it's going to converge or diverge just based on that, based on analyzing that. And we can say, well, if we have something that's non-geometric, that's not going to have the same ratio. But if we take this ratio here and take the limit as n goes to infinity, if it's equal to some number, then we can actually say whether our series is going to converge. So that's going to be using what's called the ratio test. So let me write down here, this is the ratio test. Okay, so the ratio test is going to say compute the limit as n goes to infinity of the absolute value of an plus 1 over an. So that's that ratio that I talked about previously. Just now we talked about taking the limit as n goes to infinity of this fraction. Okay. If the limit as n goes to infinity of absolute value of an plus 1 over an is equal to L, then we've got three possible outcomes, which is going to be corresponding to whether L is less than 1, L is greater than 1, or L is equal to 1. Right, so those are our three cases that we're going to break it into. So case number 1 is going to say if L is less than 1, then the sum from n equals 1 to infinity of an is absolutely convergent. And therefore convergent. So that's a very good case for us. So case number 2 is going to say if L is greater than 1, then sum from n equals 1 to infinity of an is divergent. This is also a very good case for us because it tells us exactly that our sum is divergent, and I'll say here L is greater than 1. This includes when L is infinity. So if L is infinity, then it's certainly greater than 1, and you can use case 2 here. So the case number 3 is the case that's not so good for us. If L equals 1, then the ratio test is useless. And the sum of an can be divergent or absolutely convergent or conditionally convergent. Remember, absolutely convergent means the sum of the absolute values is convergent. Conditionally convergent means that the series is convergent, but if you take the absolute values of each of the sums, then it's not convergent. So if L is equal to 1, it tells us absolutely nothing, right? So this is a very useful test as long as we fall into one of these two cases. If we fall into the third case, we're just going to have to try a different test. Okay, and I'll say here something you need to be careful of. You must use an plus 1 over an, because if you test an over an plus 1, your results will be backwards. Right, so it's very important that you remember that it's an plus 1 over an, because if you instead do an over an plus 1, then let's say it was supposed to be case 2, then you're actually going to get case 1, which is the exact opposite of what the actual truth is, right? So you need to remember that it's an plus 1 over an, and not the other way around. Okay, the second thing that I'm going to write down that we have to keep in mind, if L equals 1, you need to use a different test. Okay, so these are the two important caveats that I'll write down to this statement. Okay, now let's actually do an example trying to use this test. So test the series the sum from n equals 1 to infinity of -1 to the n times n to the power of 4 over 5 to the power of n for absolute convergence. Right. So if we actually get into case 1 here, then we'll be able to prove that it's absolutely convergent. So we're going to want to try to use this ratio test, meaning we're going to have to compute this limit. Okay, so I'll say here that we're going to be using the ratio test with an equals -1 to the n times n to the 4th over 5 to the power of n. So let's just plug it in to this formula. So we got the limit as n goes to infinity. I miswrote that. As n goes to infinity of the absolute value of an plus 1 over an. Now, you may be asking, how do we find an plus 1? Well, we just plug in n plus 1 wherever we see an n here. So we're going to do that. And here, if we do that, we're going to get the limit as n goes to infinity of the absolute value of, if we plug in n plus 1, we're going to get negative 1 to the n plus 1 times n plus 1 to the power of 4 over 5 to the n plus 1. So we're going to get this thing over, and in the denominator, we're just going to get an. So we're just going to rewrite what an is. Okay, so this is what we're trying to find. And here, if we're taking the absolute values, then we don't care actually about these parts. So this looks pretty complicated, but if we're taking the absolute values, we can get rid of all the minus signs. So we don't care about that. So now we can just rewrite this, getting rid of now the absolute values. So now we can get rid of the absolute values, since we've gotten rid of all the minus stuff. And now we can rewrite this as the limit as n goes to infinity, right? And the reason why we can get rid of the absolute value signs is that n is a positive number, so this part is positive. So we're going to rewrite this, and if we're dividing by a fraction, that's the same thing as multiplying by its reciprocal. So I'm going to rewrite this as n plus 1 to the 4th over 5 to the n plus 1, but then I'm going to multiply it by the reciprocal of this fraction, which is 5 to the power of n over n to the power of 4. Right, so I probably should have given myself a little bit more space between these two lines, but this is going to be the next line here. Okay. Now, let's go ahead and rewrite this as, yes, that's what I want to do. Let's rewrite this as the limit as n goes to infinity of 5 to the n over 5 to the n plus 1 times n plus 1 to the 4th over n to the 4th. Right. So now we've got these two paired together and we've got these two paired together. And now the reason why I did that is if we're going to multiply, so notice that 5 to the n plus 1 is the same thing as 5 times 5 to the n. So I'm going to rewrite this as the limit as n goes to infinity of 1/5 times, so 5 to the n over 5 to the n. Right, so all I did was factor out one of these copies of 5, and now I'm going to do something over here. I'm going to say, if we've got this to the 4th over this to the 4th, that's the same thing as n plus 1 over n to the power of 4. Okay, now we can say, well, 5 to the n over 5 to the n, that cancels out. And now what we've got, we're trying to find this remaining limit, and remember, whenever we're trying to deal with these fractions, we want to divide by the highest power of n in the denominator. So we're going to divide the denominator by n, and we're going to divide the numerator by n. And if we do that, we're going to get the limit as n goes to infinity of 1/5 times 1 plus 1 over n to the power of 4. The other way of seeing it is you just divide both of these things by n, you just distribute this thing, and then you get here. Right. And now if n is going to infinity, this fraction is going away, so you're actually getting 1/5, because this fraction is going to 0, so you're going to get 1/5. So 1/5 is your answer here for this. And then we said that was equal to L. So we said if L is less than 1, then our series is absolutely convergent. So our conclusion here is, so by the ratio test, this series here, I'll just say the series, but I mean this series here is absolutely convergent. That means that this series is convergent, and also if you took the absolute value of each term, meaning you got rid of this minus thing, then that's also going to be convergent. Okay. And now, so we want to do one more example, but first I'm going to have to write down a very short bit of background. Okay. So I'll write down here, recall that n factorial is the same thing as n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. Right, so we're just multiplying together all of these numbers whenever we have n factorial. So note that if we have 3 factorial over 5 factorial, then what we're going to get is going to be 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. And whenever we have this type of thing, we can just cancel this part and this part, because we divide the 3's, we divide the 2's, and, well, 1 divided by 1 is, of course, 1. So whenever we cancel those things, we're going to get 1 over 5 times 4. Right. So we're going to actually use this in the next example. So the next example is going to say, so number 2 is going to be test the convergence of the sum from n equals 1 to infinity of n to the power of n over n factorial. Okay, so here, again, we want to try using the ratio test. So I'll say here, we'll use the ratio test. So we need to compute, so it'll be the limit as n goes to infinity of, so remember, it's the limit as n goes to infinity of the absolute value of an plus 1 over an, which means you have to plug in n plus 1 into this function and then divide by the original function. So if you do that, we're going to have n plus 1 to the power of n plus 1 over, so I'm just going to first compute the fraction, right? So I'll just first do that because that'll be a little bit simpler for us, over n plus 1 factorial. So that's what happens if you plug in n plus 1, and then you divide by when you just plug in n, which is going to be this. So we're trying to compute what this fraction is, because then we're going to plug it in to this limit. So first we need to compute this, and I'll rewrite this. If you're dividing by a fraction, you're multiplying by its reciprocal. So this is, this is equal to n plus 1 to the power of n plus 1 over n plus 1 factorial times, this will be n factorial over n to the power of n. Okay. now I want to rewrite this. So I'll just pull out a factor of n plus 1 here, and I'll pull out a factor of n plus 1 here. So if I do that, then we're going to get n plus 1 times n plus 1 to the power of n. That's what happens if I pull out one factor of n plus 1 in the numerator. And if I do that in the denominator, then we're going to get n plus 1 times n factorial, right? Because n factorial is multiplying all the numbers less than or equal to n. And here, if you multiply that by n plus 1, then you've actually got n plus 1 factorial. And this is times n factorial over n to the power of n. Now, let's look at what cancels. So this n plus 1 is going to cancel with this n plus 1. And this n factorial is going to cancel with this n factorial. So we're just left with this fraction here. So we're left with n plus 1 to the power of n over n to the power of n, which we can simplify as n plus 1 over n to the power of n, right? Because they both have the same exponent, so we can do this. And now we can go ahead and rewrite this if we wanted to as 1 plus 1 over n to the power of n. Okay, so we can write here that the limit as n goes to infinity of an plus 1 over an, which is the same thing as the absolute value of this, which is the same thing as n plus 1 to the n plus 1 over n plus 1 factorial, all of this over n to the n over n factorial. So we're dividing the two fractions. Now, this limit, we said we simplified the inside to be this. So it's the limit as n goes to infinity. Note this is going to be positive since n is positive. So I'll just drop the absolute value symbols. So 1 plus 1 over n to the power of n. And let me write, this is equal to, so this is actually just a fact. So this is just a fact that this is equal to the number e. Right? This is actually one of the ways to define e. So one of the ways you can define e is by taking it to be exactly this limit. And this actually gives you exactly what e is equal to. So this is actually equal to e. And we can say since the limit as n goes to infinity of an plus 1 over an, the absolute value, is equal to e, which is greater than 1. The series, yes. Yes, that's what I'm going to say. Yes, the series diverges. Right, because e is 2.7 something, and that's bigger than 1, so just using the ratio test, we can say that the series diverges. Okay, so what I'll say here in conclusion is, let me use a color other than that. Oh boy. The ratio test is very useful when an has an n in the exponent and or factorial. Okay. Now, our next question is, what if we have a different kind of series? Okay, so we can ask, what about series like, so let's say we had the sum from n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the power of n, or let's say we had the sum from n equals 1 to infinity of n plus 1 over n to the power of 2n. Right? So I said the ratio test is useful whenever we have these n's in the exponents, but if the whole thing is raised to the power of n, or in this case 2n, then it actually becomes more complicated. Because whenever you're trying to compute an plus 1 over an, it's going to become very difficult if you've got these exponents on the outside. So that's when we're going to actually need a different tool. So I'll say here, the ratio test here would suck to use. Note that the entire an is being raised to an exponent that involves n. We use the root test on series like this. Okay, so now we're going to use the root test. So the root test is going to say, suppose the, oh shoot, that's not what I meant, right? Suppose the limit as n goes to infinity of the nth root of the absolute value of an is equal to L. Okay, now the first statement here is going to be if L is less than 1, then the sum of an is absolutely convergent. And remember, if something's absolutely convergent, then it's also convergent. So that's a very good case for us. Number 2 is going to say if L is greater than 1 or L is infinite, then the sum of an is divergent. And case number 3 is if L equals 1, then this test is useless. Okay, and we'll draw a little frowny face to denote the fact that we're sad that it's useless in that case. Okay, so this again is a test that's very good sometimes, but sometimes it just doesn't tell us anything. And I'll say for the next problem, I keep trying to use that color and it's not working. The next problem, recall that or really for all of the problems, recall that the nth root of the absolute value of an equals the absolute value of an to the power of 1 over n. Right, so we can always rewrite this nth root as as a fractional exponent. Okay, so let's now do another example. So the second to last example, we just got 2 examples left. Okay. So example number 3 is going to say test the convergence of the sum from n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the power of n. We're trying to test whether this is convergent, absolutely convergent, divergent. Trying to see what it is. Okay, so we want to try, so let me say here, the whole point of the root test is in getting rid of the n in the exponent. Right, so we see that this thing has got an n in the exponent, so that means we're probably actually going to want to use the root test. So we'll say here that the nth root of 2n plus 3 over 3n plus 2 to the power of n, well, if you try to take that, well, the nth root is something to the power of n, that's just going to cancel out. So we're just going to get 2n plus 3 over 3n plus 2. So that's why we like the root test, because we can get rid of these weird exponents. So we can say here, so in the root test, we need to evaluate this limit. So, and since n is greater than or equal to 1, then this is always positive, so we don't need to worry about these absolute value symbols. So we'll say the limit as n goes to infinity of the square root, sorry, not the square root, the nth root of the absolute value of an is going to be equal to the limit as n goes to infinity of 2n plus 3 over 3n plus 2. Okay. And now, if we take this limit, now notice the way we take these limits is, of course, we need to divide both sides by n, which is the highest power of n in the denominator. So it's the limit as n goes to infinity of 2 plus 3 over n over 3 plus 2 over n. Okay, and now notice n is going towards infinity, so these two fractions are going away. And now we're just going to get that this is 2/3. Okay, so now remember this is L. This is capital L. So now if L is 2/3, it's certainly less than 1. So we know that it's absolutely convergent, which is very good. So the root test gives that our original series is absolutely convergent. Okay, so that's very good. So the root test actually gave us a very strong condition. Not only is this thing convergent, it's absolutely convergent. But notice, well, this thing is always positive anyway, so saying it's convergent is actually the same thing as saying it's absolutely convergent, because every term in this series is positive. Okay. Now, we can move on to our last example. Okay. So example number 4 is going to say test the convergence of the sum from n equals 1 to infinity of n plus 1 over n to the power of 2n. So again, we see we have this weird exponent. So, or we see that we have n in the exponent is what I meant to say. The whole thing is being raised to the power of n, or it's actually 2n, but n is inside of the exponent. So that's our clue that we might want to use the root test. So here let's just compute what the nth root is going to be. So the nth root of n plus 1 over n to the power of 2n. So I would encourage you to work this out on your own, but this is 1 over n, and this is 2n. So you just multiply the exponent with 1 over n times 2n. This is n plus 1 over n to the power of 2. Okay, and we can rewrite this as 1 plus 1 over n to the power of 2. Okay, so using the root test, so we're going to get that the limit as n goes to infinity of 1 plus 1 over n to the power of 2. So remember, we're taking the limit of the square root, which we already said was this. So this is what we're taking, this limit. And if n is going to infinity, then, well, let's just rewrite this first as the limit as n goes to infinity of 1 plus 1 over n squared. And now, since we've done that, we can just say, well, n is going to infinity, so this fraction is going away. So this is just becoming 1 squared, which is 1. Okay, so our answer here that we got was 1. So using the root test, if we get L equals 1, we see that that was actually useless. So the root test is not going to give us anything here. So it turns out we actually can't use the root test for this problem. That's the first thing we wanted to check because the exponent involves n, but it turns out it's not going to work. So whenever a test fails, oftentimes our answer, as I said earlier, is trying to test for divergence. So let's use the test for divergence, which, remember, was saying we just take the limit as n goes to infinity of this thing, and if it either doesn't exist or is non-zero, then it's divergent. So that's what we're going to do. So let's see here, limit as n goes to infinity of this thing here. So it's n plus 1 over n to the power of 2n. But we can actually rewrite this. So this, if you write something to the power of 2n, you can rewrite it as n plus 1 over n to the power of n to the power of 2, right? Because if you raise this thing to the power of 2, it's the same thing as just multiplying the exponent, so you get the same thing. But now, if we're taking the limit of this thing squared, we can do the same thing we did here, where we pull the 2 on the outside. We're going to rewrite this as the limit as n goes to infinity. Or sorry, I messed up the writing on this. This is this limit of n plus 1 over n to the power of n squared. Okay, but remember, we can rewrite this inside part as the limit as n goes to infinity of 1 plus 1 over n to the power of n squared. And remember, we said if we've got 1 plus 1 over n to the power of n, and we're taking the limit as n is going to infinity, that's the definition of the number e. So this is e to the power of 2, and that is certainly not equal to 0. So remember, the test for divergence said if this either does not exist or is not equal to 0, then it's divergent. So the test for divergence gives that the series is divergent. And I'll just say a brief word on why the test for divergence works. Let's say that this limit is non-zero, then eventually what this is saying is each term is going to look like e squared. So you're just going to keep adding something that looks like e squared to itself, and if you're doing that infinitely many times, well, since that's a non-zero number, you're going to end up getting something that goes towards infinity, right? Because if you keep adding a positive number to itself infinitely many times, you're going to go towards infinity. So that's why the test for divergence says if this is non-zero or doesn't exist, this limit of this right here, this term on the inside, this an, if this limit is non-zero, then it's divergent.